So the next part that that I'm skipping over in terms of slides is something that we call the adaptive enrichment design. So it's very, very similar to what we did before. The only difference is, before we said that we were going to choose a treatment dose. Yeah. In this case, what we are saying is we're going to choose a population. Yeah. So for example, you have, one of the most common example is, the presence of a protein called HER2/neu, for in some patients, breast cancer patients, and only patients that have HER2/neu are respond to a treatment called Herceptin. Okay, and people patients that don't have HER2/neu, they don't respond to Herceptin. Okay, so now what you want to do is you want to select, enrich your population. You want to say, hey, I want to bring in people only who are HER2/neu, so that my drug has a best chance of succeeding. So that eventually when I sell it, I will sell it only to the people who are HER2/neu. So going from one size fits all, here is a drug for everybody, everybody can take it, like aspirin or Crocin for headache, everybody can take it, to tailoring it and saying only people who are HER2/neu can take Herceptin. That's the motivation. That's what we want to try and do. Okay, so it's very similar to the concept that we had before, which is that instead of treatments, here we'll have populations. Populations that are biomarker positive, populations that are biomarker negative, and we want to try and only include people who are biomarker positive. So in stage 1, what we would do is we would try and identify, does the drug work better in biomarker positive people or biomarker negative people or the whole population? Yeah. And then depending on that, we would go ahead and say, either we will test the full population or we'll test only the subpopulation who are biomarker positive. Okay. So same thing as that. So subpopulation S, full population F. Okay. And again, we have the same multiplicity issues, whether we test in full, whether we test in S. We have looks, once we do a look, we want to adapt whether we want to only enrich and look at the subpopulation or we want to look at everybody. Okay, so everything is similar, similar Venn diagrams as before. Yeah, and then we have this case study, and you can take a look at this. It's a very, very nice case study where this is your decision rule at the interim analysis. Is if both the predictive power for both the full and the subpopulation is less than 35%, then you stop for futility. If the predictive power in the full population is greater than 35%, then you continue to the full population. Yeah. If only the subpopulation predictive power is greater than 35%, then you adapt and only go to the subpopulation. Yeah. And these are the different decision rules. Okay. But this is just a more complex, extension of what we did before when we looked at 2 treatment arms and only if, chose one of them and dropped the other one and then did the combination test. So we'll do exactly the same sets of things here as well. Okay. So now let's look at in phase 3, we have specifically 2 different types of things called group sequential design and sample size re-estimation. So we'll focus on those 2 concepts. Yeah. So what happens in a group sequential design is, when you're running a very large phase 3 study, you want to take a look at the study at different time points. So let us say the study is going to run for 5 or 6 years. You're not going to wait 5 or 6 years to look at the data, right? So you want to look at the data, let's say at 2 years, at 4 years, and then finally at 6 years, something like that. Okay. So you may want to take a look at the study at specific time points. Okay. And so you would use something called a group sequential design. And what you do in the group sequential design is you take your overall alpha, like the Bonferroni, okay, and you split it, okay, between all the different interim looks. Okay. The only adaptation that is possible in a group sequential design is to continue the study or stop the study for either futility or efficacy. Okay. You can't do anything else. You can't increase the sample size. You can't do any of that stuff. Okay. So let us say that you're expecting 1,000 patients in the study. You take a look at when 250 patients are in, when 500 patients are in, when 750 patients are in. Okay. And you can either stop at 250, at 500, or at 750. If not, then you go all the way to 1,000 and you finish the study. Okay, so that's the only adaptation. You can stop early, but that's it. Okay, no other adaptations like increasing sample size, etc. is allowed. Okay, now how do you split this alpha? Okay, now we learned Bonferroni, and it said, okay, I'm going to do 4 tests. I'm going to look at it at 250, at 500, at 750, and then at final. So I'll take my 0.05 and I'll split it 4 ways. Yeah? So I'll do each one at 0.0125. Each look I will test. Yeah, that's one way of doing it. Okay, but that may not be the most sensible way of doing it, right? Because at the first look, when you only have 250 patients in, you have very little information. So when you have little information, you don't want to spend a lot of your alpha, right? So you want to spend little alpha in the beginning, and you want to spend most of your alpha in the end when you have a lot more information, correct? So this splitting or spending of alpha can be changed, and that is called a alpha spending function. So for example, these are 2 different alpha spending functions. Okay, in this case, which is called the O'Brien-Fleming alpha spending function, you're saying that I'm going to spend my alpha, which is a blue line. So until about 50% of the data is in, I'm hardly spending any alpha. Do you see that? This is a 50% point, and I'm spending less than 0.0025 alpha. Very little. So I keep most of my alpha for the end. Same thing with beta. Okay. So you can have an alpha spending function and a beta spending function. On the other hand, for plan 2, which is a Pocock type of spending plan, what you would have is, you say that I'm going to spend the same amount of alpha irrespective of what the look is. So at 0.025 here, the amount of alpha I spend is roughly also 0.025. Okay, so I spend same amount of alpha and beta in the beginning of the study or at the end of the study. Okay, you can do whichever. You just have to upfront say what you're going to be doing. Okay, it doesn't matter what you do. You can either choose O'Brien-Fleming or you can choose Pocock. So in a clinical trial setting, there are times when you would choose O'Brien-Fleming. There are times when you would choose Pocock. Yeah. And once you have your alpha spending, these are your boundaries. Okay. As you can see, these are the boundaries for your alpha, and these are your boundaries for beta. Okay. So for O'Brien-Fleming, what you're saying is that I'm spending very little alpha, right? So which means my critical value has to be very high. So only if my critical value is in this blue area, okay, am I going to reject? So normally what do you expect your critical value to be? Roughly around 2, right? For you to be significant. But for you to be significant at this look, your critical value doesn't have to be 2. It has to be greater than 4.25 or something. Okay. And it's 2-sided. So you see that mirrored on both sides. Okay. So this is what you would do in O'Brien-Fleming. Whereas in Pocock, you're saying that it is the same irrespective of when I look at it. Okay. So I start with 2.4 and I am spending 0.0125 every time. So at any look, it has to be greater than 2.45. Okay. So you can see how it is, right? If you're very sure, very confident that your drug works, then you want to use this, correct? Because then if your alpha is greater than just 2. If your alpha, if your critical value is just 2.5, then you can already stop and say your trial is successful, and you can stop early if you're very, very confident that your drug works. Yeah. But if you're not very confident your drug works, then you want to use something like an O'Brien-Fleming. Does that make sense? Yeah. So once you have, this is all planning. So this is how you define. Once you've done this, this is what happens when you're actually running your study. So these are your test statistics at different looks. Can you see these numbers? Yeah. So for example, at look 1, your test statistic is 1.8. So if you were using an O'Brien-Fleming boundary at look 1 at 1.8, would you reject your null hypothesis and stop the study or no? You can use the chat window to tell me what you would do. Your test statistic is 1.8, right? If your test statistic is greater than 2, then what is your p-value? Less than 0.05, correct? In this case, your test statistic is 1.8, okay? So it's lower than 2, okay? If you were to use O'Brien-Fleming, would you stop your study at this point and say that your drug works? Would you stop for efficacy? No, right? If you remember, how was this? This was your boundary. Remember, and what did we say? Your boundary had to be very high. It had to be, a critical value had to be more than 4 point something for you to stop, correct? So you can see that down here as well. The blue dots is your boundary region, okay? Your green dots are your test statistic that you see in the particular study. So the first value is 1.8. Is 1.8 greater than this blue line, blue dot? No, right? So which means you continue. The second value is 1.9. Now your blue dot is coming down. Your green dot is going up. But is the green dot higher than your blue dot? No, it is not. So you continue with the study. The third test statistic is 2.0. Okay. Now your blue dot is really come low because at the final your blue dot has to be close to 2, correct? So now your blue dot is really close, but your green dot is still slightly below your blue dot. Yeah, because what is your blue dot value? 2.336. Your green dot value is 2. 2 is still less than 2.336. So you still continue. And what happens at the last stage? At the last look, your green dot value is 2.1. Okay. And now you can see that your blue dot value is 2.019. So now your green dot is higher, larger than your blue dot. And so at the end of the study, you can stop and you can say that your drug is better than placebo, or that you reject the null hypothesis. Okay. In this case, if your green dot had been greater than 2.336, let's say a green dot was 2.4, which is right around here. If that had been the case, then you could have stopped at the third look and said that your drug is better than placebo.